Welcome back to our whiteboard. I just want to start this out once again with this picture of reflection. Something I alluded to in the last video, but something that should be said. Notice here, I didn't draw in any normal lines. So what would be true about the normal lines that we would draw in this situation? Yep, hopefully you said that they go in along our incident ray, right? Here would be the normal line there. Here would be the normal line there. And so the reason why these rays bounce directly back is because the angle of incidence here would be 0 degrees, and therefore the angle of reflection would be 0 degrees. What do you think is the most common error that people have with this? And if you said that people say that the angle of incidence is 90, you're right. It's not, because we don't measure angles here to the boundary. We measure everything to the normal line. Now, the focus actually of what I want to talk about here is with curved boundaries. So here we go. Let's look at what happens here with a curved boundary. So if I draw an incident ray, so here we go. I'm going to draw a ray perpendicular to my wavefronts until I get to the boundary. Now, remember what the law of reflection says. The law of reflection says that you have to examine this at each point. So here we go. If I wanted to do the reflection here, what I would have to do is construct a normal. But how do I construct a normal here? Because I've got a curved figure. Well, hopefully what you figured out is what I have to look at is a tangent line to the curve at that point, and my normal line is going to be perpendicular to that tangent. Okay? So let me draw in that normal line there. Boom. And so now, if I wanted to measure what the angle of incidence is, I can do that. So let's just put that down there. And it looks like my angle of incidence is 10, 20, 30, 40, 2 degrees. And therefore 10, 20, 30, 40, 2 degrees would be my angle of reflection. And I will draw that in. Okay. Now, if I looked at a different ray, though, say one right here, okay, notice I would draw that in till it got to the boundary, but then hopefully what you'll realize then is because the curve is slightly different at that point, the tangent at that point is slightly different. So if I draw in a tangent here, and then draw in a normal line, the two normal lines that I drew are not going to be parallel to each other. Boom, right? We're at a slight angle to each other. Notice before, when we drew multiple incident rays, because the boundary was flat, the two normal lines were parallel to each other. And therefore, these two parallel incident rays were parallel reflected rays. So that means we're not going to get the same parallelism here because the normal lines are no longer identical to one another. So if I measure that incident angle, we can see 10, 20, 32, it's quite different. And then if I draw the reflected ray, 10, 20, 32, boom, right? I would have the ray going off in this direction like this. Now, notice, unlike in the video, I'm not getting everything to converge really nicely because this is not really a parabola. It's just some random shape that Word generated for me. So we're going to look at what happens with the parabola, not by doing too precise measurements, but by, I'm going to just draw a separate picture for you to see. So let's look at that. What we saw in the video was the following, that if I had a parabolic boundary, right, and I'll just draw it this way. Let's pretend that's a parabola. It's not. That what would happen here is that if I had a bunch of rays that were all parallel to each other, okay, that the normal lines here, because they are not parallel, would bounce these rays all in different directions. And what we saw in the video is that, say, for example, here's this one's reflected ray, and if this is this one's reflected ray, and that's that one's reflected ray, and then that's that one's, and that's that one's. That's what was going on, that all the reflected rays were meeting at the focal point. So what we can say here is that when you have straight waves coming in, straight waves in, that means that you have parallel incident rays, that they meet at the focal point. Okay? And that's what happens with parabolic boundaries, which is kind of cool. Now, in the same way that if I make circular waves at the focus, I get straight waves out. And we saw that very clearly in the video. I did want to also mention what was happening there with when the boundary was circular, because it was slightly different. With a circular boundary, right, I'm going to draw it a little bit more. If I made straight wave, or I made circular waves at some point here, I got straight waves for part of it, but then it curved outwards at the edges, right? And the reason why I got the straight part is because we said that a circle approximates a parabola for much of the arc, right? So these edging effects are what are called spherical aberration. And spherical aberration is a distortion due to the use of circles rather than parabolas, because a circle does not have a focal point in the same way that a parabola has a focal point. And you may ask then, if you get this sort of crappy wave with a circle, why would you use a circle rather than a parabola if a parabola is perfect? I'm going to tell you it's because parabolas are really, really, really hard to engineer, and circles are very simple to engineer. So if you don't need precise instrumentation, oftentimes you make do and you just deal with the spherical aberration, right? That comes up quite often in a lot of wave applications, that we just use this approximation of the sphere for this for the parabola because of how difficult it is to make parabolas. Now, let's look at another curve, because the curve that we looked at here, this parabolic boundary, to go back here, we were looking at what we'll call a concave boundary, meaning that the curvature was towards the wave coming in. If we instead look at the following, a convex boundary, I'm just going to sketch this. I'm not going to worry too much about measuring the angle. If I looked at a couple of rays coming in, boom, 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 what would be true about the normal lines here? Well, if you said that the normal lines here also were not parallel to each other, you'd be correct. And that's why these rays are not going to reflect off parallel to each other. In fact, what I hope you see is that here our rays diverge from each other. They go away from each other. And in fact, if I were to draw the reflected wavefronts, they would take the shape of the boundary, okay? So with flat waves, we saw in the video that the shape of the wave coming in was pretty much the shape of the wave coming out. But with convex and concave boundaries, the shape of the wave is changed rather dramatically because of its interaction with the wave. So there you go. The law of reflection is still true because I can do the law of reflection at each individual point. And it doesn't matter what the shape of the boundary is. You just have to look at what is the normal at that point to the boundary. And we saw how parabolic boundaries worked, how circular boundaries work, whether they're convex or concave. And so that's everything that you need to know about reflection in 2 dimensions.